So let's go ahead and get started. So I'm going to just go through the homework real quickly. This kind of lays out the basic way that you're going to find resistance for just about any type of system. The only difference is really going to be what type of geometry that you have. So that's going to change what your area is going to be and what your limits of integration might be. So the first thing that I wanted you to do was write down and explain all of the pieces of the microscopic form of Ohm's law. And that's just to say that E vector is going to be equal to rho times J. Okay. Now, some important things about this. We're already familiar with the left-hand side. This is just an electric field. The right-hand side has two new things, and looking at this you might say, well, I've seen rho before, and it's just kind of a historical accident and a little bit unfortunate that in this class we use rho for two different things. So the first time that we used rho to talk about a volume charge density. This rho in the microscopic form of Ohm's law is actually the resistivity. So this is the resistivity. Okay. The last portion of this equation is what's called the current density. And this can be related to the current in the next portion of the homework, and that's just to say that the current, I, is going to be equal to the flux of the current density. So if you think about current density as some current per area, and you add up all of that current per area in the direction of some cross-sectional area, that gives you what the total current in some resistor is. So the next thing that I wanted you guys to do is to show in general how the macroscopic form of Ohm's law can be obtained from the microscopic form of Ohm's law. So the macroscopic form of Ohm's law just says that V is equal to IR. And so we want to take these two pieces that we have here and derive this equation here. So the first thing that we can see is that in order to get from the microscopic form to the macroscopic form, we're going to have to use our definition of the difference in electric potential. And we're going to have to use this definition of the current density in order to get this electric field in terms of the current instead of the current density. So if we first start by looking at this equation here, what we can say is that if J is in the same direction as dA, and it doesn't vary over the same variables that dA does, then this can be reduced so that I is just going to be equal to J times some cross-sectional area. And then from this, what we can do is we can say that J is just going to be equal to I divided by A, right? And this should seem to make sense because what I'm saying is that the current density is going to be equal to the current divided by the area. So now that we have this, what we can do is we can plug it into our microscopic form of Ohm's law. And that's just to say that as a magnitude, or I could recover the vector by saying E vector is going to be equal to rho times I divided by A times some unit vector we can say is in the x hat direction, just for this example. And then, in order to find what the difference in electric potential is, I can say that delta V is going to be equal to the negative integral of E dot dl from some R1 to some R2. And just for this example, we'll say that this is going to go from some 0 to L. We'll see explicitly why that's the case when we do our actual example here. So this is going to be equal to the negative integral of rho I divided by A x hat dot x hat dx from 0 to L. And so this is going to give us a rho I divided by A times L with a negative sign. Now, because resistance, like capacitance, is always defined to be a positive quantity, I'm just going to take an absolute value of this and then we can compare it to our macroscopic form of Ohm's law if I rearrange it a little bit. And so that's to say that V is going to be equal to I times parentheses rho L divided by A. And for some resistor of this form, so if we have some resistor like this is the cross-sectional area A and some length of L, and the current is going to flow from left to right. This says then that the resistance is just going to be equal to rho L divided by A. Okay? And so if you've taken some physics classes before, you might have even seen the microscopic form of Ohm's law. Who's seen this one before? Maybe a handful? Nobody's seen this one before. Okay. But you've definitely seen this before, right? Everybody's seen this before. And you've probably seen this as well. Okay. So this is how we can talk about what the electric field is on the inside of some resistor in terms of the resistivity and the current density, and how we can use that information in association with the definition of the current density in order to derive the macroscopic form of Ohm's law, the one that we're more familiar with. Okay. Any questions about what I've done here so far? Yeah?
Can you talk a little bit about units?
Sure. So I'm going to be really cavalier with this. So the electric field is going to have units of newtons per coulomb, right? So that's not a W, it's an N. So E has units of newtons per coulomb. The current density is going to be, by definition, some current divided by area. And current has units of charge, so coulombs per second. Right. And so J is going to be coulomb per second times an area, and then we can figure out what the units of resistivity need to be in order for this equation to be balanced. And so that's to say then that the resistivity is going to have units of second area. Second area Newton per coulomb squared. So it's a little bit of a mess if you do it in SI. But it's just applying rules for dimensional analysis. So you say, okay, well, I know what an electric field, what the units of an electric field should be from the first portion of the Lorentz force law, right? And then a current density, I know it's going to be some current per area, and then I can use that to find what the units of resistivity are. Now, the way that we could do this a little bit differently, because in electrodynamics, you typically don't talk about newtons, you talk about voltages. So you could write this instead and say that because V is equal to the integral of E dot dl, the electric field, if this has a unit of volts, the electric field is going to be in units of volts per meter. Okay, and then you can write this in terms of volts instead if you wanted to. Okay, other questions? Okay, so let's get into the example that we had. So in the notes, what I did was I basically did the same derivation that I had here, because what I assumed was I had the arrangement that I had drawn up here, where you have some cross-sectional area of A. I actually think I said it was some radius of lowercase a with some constant resistivity. But you can apply this same process to talk about how can I calculate the resistance if instead of having some constant resistivity, I have some resistivity that varies as a function of length. So this is to say that rho as a function of x is equal to rho 0 x squared divided by L squared if this is the arrangement that I have. So this is L. Let me make sure I'm just doing this the same exact way. So this is the cross-sectional area A, and then this is rho as a function of x. Okay. So what that means is as you move from left to right, there's more and more resistivity as you go, so that it follows this polynomial here. So in order to do this, we can start out by writing down the pertinent equation. So E is equal to rho times J, and I is equal to the integral of J dot dA. Now, I want to pause here for a second, because this is going to follow exactly the same form as this, but I could have given you a different question, which is actually what I did for the work today, where instead of having the current flow from left to right, I have some current that's going to flow outwards like this. And then this dA that I have is the area that it flows through, and so in this case, this is going to be it's almost like drawing a Gaussian surface, right? Because I know my current's going to flow from the inner surface to the outer surface, so that's the direction that J is going to go. And dA is in that same direction, so when I sum over my dAs, this is just going to be 2 pi r times L. So as always with these types of questions, you have to be very careful with the type of geometry that you have. And we'll see this. In the homework for tonight, I do the same thing with a sphere. So to come back to this exact problem, this I is equal to the integral of j dot dA is just going to give me identically I is equal to j times a, or j is equal to I divided by a. And so this equation can be written as E vector is equal to rho as a function of x times I divided by a. And I want to find what the difference in electric potential is between this side and this side. And so that's to say that delta V is going to be equal to the negative integral of E vector dot dl from 0 to L. And so this is going to be equal to, I can pull out my I over A, so this is minus I over A. Integral rho 0 x squared over L squared times a dx from 0 to L. So when I do this integral, I'm going to have an x cubed evaluated at 0 and evaluated at L. And so this is going to be equal to x cubed over 3, that is. So this is going to be a minus I times rho 0 3a L squared times a L cubed, right? So I can get rid of 2 factors of L, and then this says that this is going to be equal to minus, I'm going to put the I by itself, and so this is going to be rho 0 L divided by 3a. And this is delta V. And because what we want to do is we want to say that the resistance is constant, I can just take an absolute value here and say then that my resistance R is just going to be equal to rho 0 L divided by 3A. Okay? Any questions about this? Okay. So like I said, I just laid out the process that you go through here. You write down microscopic form of Ohm's law, you write down what the current is in terms of the current density, and then you write down that the relationship between or the definition of the difference in electric potential. And then you can turn the crank for whatever geometry that you have. Okay? So everybody's good with this? Yeah.
There would never be a situation where you would keep the x cubed and L squared in the bottom. Would the length dimension on top and the length dimension on the bottom always end up being the same for calculating the resistance?
Well, so you could have done this a little bit differently, and so instead of saying that rho as a function of x is equal to rho 0 times something, I could have said that this is equal to alpha times x squared, so that whatever the units of alpha are such that it cancels to a resistivity. So the units of alpha in this case are actually resistivity per length squared. But you'll notice that a lot of times when I'm writing these kinds of questions, I have my x squared and I have my L squared. So I do that for a particular reason, and that's so that this has units of resistivity and this portion is dimensionless. But you could foreseeably write something in terms of some constant that is not resistivity. It just means that whatever that constant is, it has to have the units such that it cancels the units that are on the right side to give you something that is resistivity. Okay? Other questions? Okay, so go ahead and get to work on the classwork for today, and we'll come around and answer your questions as you have them.